There is a claim in cosmology so bold it can seem like hubris, and yet it is among the best-tested statements in all of science, that we know in quantitative detail what the universe was doing when it was between 1 second and a few minutes old. That knowledge is the achievement of Big Bang Nucleosynthesis, the theory of how the lightest atomic nuclei were forged in the first minutes of cosmic history. While the whole universe was a furnace cooling through billions of degrees, it stands as one of the 3 great observational pillars of the hot Big Bang, alongside the expansion of the universe and the microwave background. And of the 3 it reaches deepest into the past, for it probes an era governed entirely by physics we can measure in the laboratory. In effect, nucleosynthesis turns the newborn universe into a working experiment, whose output, the primordial abundances of the light elements, we can still read off the sky billions of years later. Picture the universe at an age of 1 second, a searing plasma of photons, electrons, neutrinos, and a trace of protons and neutrons, at a temperature of some 10 billion degrees. As this fireball expanded and cooled over the next few minutes, a brief window opened in which nuclear reactions could build the first compound nuclei. What emerged were the lightest elements: deuterium, a heavy form of hydrogen, 2 forms of helium, and a trace of lithium. And then it stopped. When the reactions froze out, the universe had been left with a chemical composition of roughly 3/4 hydrogen and 1/4 helium by mass, with everything heavier amounting to a mere sprinkling. That primordial mixture is the floor on which all later chemistry was built, the raw material handed to the first stars, which would take hundreds of millions of years to forge the carbon, oxygen, and iron that the Big Bang itself could not. Why did nucleosynthesis halt so abruptly at helium, leaving the universe almost barren of heavier elements? The answer lies in a curious gap in the ladder of nuclei. There exists no stable nucleus with a mass of 5, and none with a mass of 8. Try to add a particle to helium or to fuse 2 helium nuclei together, and the product falls apart almost instantly. In the hearts of stars, this mass-8 gap is bridged by a rare triple collision that catches 3 helium nuclei at once to make carbon, but that trick demands the enormous densities and long ages available in a stellar core, conditions utterly absent from the rapidly thinning early universe. And so cosmic nucleosynthesis essentially ended at helium, with only a faint leakage past the gaps to make lithium. The cosmos was handed over to its first generation of stars as a nearly pure hydrogen and helium mixture, almost devoid of the elements on which planets and life would one day depend. The idea that the elements were cooked in the early universe dates to the 1940s and the restless imagination of George Gamow. Its founding document is a famous paper of 1948, and here Gamow, an incorrigible joker, could not resist adding the name of Hans Bethe to those of his student Ralph Alpher and himself, purely so that the authors, Alpher, Bethe, and Gamow, would echo the first 3 letters of the Greek alphabet. The details of their scheme were wrong. It could not vault the mass gaps to build the heavy elements, which are in fact made in stars. But it correctly identified the early universe as the birthplace of the light elements, and in related work, it even predicted that the cosmos should still be bathed in relic radiation a few degrees above absolute zero, a stunning anticipation of the microwave background, then entirely overlooked. Over the following decades, ever more precise nuclear measurements, and finally, the satellite mapping of the microwave background, turned the theory into a science of extraordinary precision. To understand what the Big Bang made, we must follow one number above all: the ratio of neutrons to protons. For almost every neutron present when nuclear burning began would end up locked inside helium nucleus, so that ratio effectively fixes the helium yield. In the first fraction of a second, at temperatures far above 10 billion degrees, protons and neutrons were freely and rapidly interconverted by the weak nuclear force and their relative numbers held at a value set purely by the tiny difference in their masses, the neutron being just slightly heavier than the proton. At the highest temperatures, this meant roughly equal numbers of each. But as the universe cooled, that small mass difference began to tell, tilting the balance steadily in favor of the lighter proton, so that neutrons grew progressively rarer with every drop in temperature. This delicate balance could only be maintained so long as the weak interactions kept pace with the expansion of the universe, and they did not keep pace for long. The weak reaction rates fall extraordinarily steeply as the temperature drops far faster than the expansion rate does, so at a well-defined moment, around 1 second at a temperature near 0.8 of a million electron volts, they simply fell behind. The interconversion of protons and neutrons effectively switched off, and the ratio froze at that instant, about 1 neutron for every 6 protons. But the story was not quite over, for the free neutron is unstable and slowly decays. In the few minutes that elapsed before nuclear burning could begin, a modest fraction of those frozen neutrons decayed away, easing the ratio down from about 1 in 6 toward 1 in 7. It is this final figure, roughly 1 neutron to every 7 protons, that would set the amount of helium in the universe. Why, though, was there a delay of minutes at all? If the plasma was already cool enough to hold nuclei together, why did burning not begin the instant the neutrons froze out? The answer is a beautiful piece of cosmic kinetics known as the deuterium bottleneck. The very first step in building any nucleus is to fuse a proton and a neutron into deuterium, but deuterium is only feebly bound, and there lay the obstacle. The early universe contained roughly 2 billion photons for every single baryon, and even after the average photon had cooled well below deuterium's binding energy, the sheer number of them meant that the rare, high-energy photons in the tail of the distribution were still numerous enough to blast apart every deuterium nucleus the instant it formed. Deuterium simply could not accumulate. Until it did, nothing further could be built, and the whole reaction chain stood starved of its very first ingredient. The bottleneck held until the temperature had fallen to about 7/100th of a million electron volts, roughly 1 billion degrees, a few minutes into cosmic history. Below that threshold, the destroying photons finally became too few and too feeble, and the logjam broke. What followed was sudden and dramatic. Deuterium abundance shot upward by orders of magnitude, and the entire downstream network of reactions, long held in check, fired almost all at once. Nucleosynthesis ran nearly to completion within a few minutes, after which the relentless fall in density and temperature quenched all the reactions and froze the abundances at their final relic values. The deuterium bottleneck thus acted as a delayed release trigger, holding the whole process back until a sharp temperature threshold was crossed, and then releasing it in a burst. And the small residue of deuterium that survived unburned would become, as we shall see, one of the most powerful diagnostic tools in all of cosmology. Once the bottleneck broke, a swift cascade of reactions channeled the deuterium onward into helium-4, which acts as a kind of nuclear attractor. Of all the light nuclei, it is by far the most tightly bound, and so it is the strongly preferred destination. To an excellent approximation, every neutron that survived to this moment was swept up into a helium nucleus, each of which holds 2 neutrons and 2 protons. This leads to a wonderfully simple estimate of the cosmic helium abundance. Take 1 neutron for every 7 protons, pair each neutron with a proton to build helium, and count what fraction of the total mass ends up in those helium nuclei. The arithmetic yields very nearly 1/4, and so the theory predicts, from the barest handful of inputs, that the universe should emerge from its first minutes with about 25% of its ordinary matter in the form of helium and 75% as hydrogen. Detailed computation sharpens this to a helium mass fraction of very close to 0.247. A subtle but crucial feature of this helium prediction is how little it depends on the density of matter in the universe. Once the bottleneck opens, the reactions run essentially to completion no matter the exact density, so the helium yield is governed almost entirely by that neutron-to-proton ratio, which was set by the weak force and the expansion rate, not by how many baryons there happen to be. Helium-4 therefore rises only very gently, logarithmically, with the cosmic density of ordinary matter. This makes it a poor gauge of that density, but an exquisite gauge of something else, the rate at which the universe was expanding during the first second, and hence the number of particle species contributing to that expansion. Helium is, in effect, a cosmic speedometer for the newborn universe, and its insensitivity to density throws into sharp relief the opposite behavior of deuterium, which turns out to be the finest density gauge of all. The master parameter of the whole theory is the ratio of baryons to photons, the number of ordinary matter particles for each particle of light in the universe. Because the microwave background fixes the number of photons with great precision, this ratio is a direct measure of the cosmic density of ordinary matter, and it is a startlingly small number. Only about 6 baryons for every 10 billion photons, one particle of matter adrift in a sea of more than 1.5 billion photons. That tiny figure is the seed of all cosmic structure, and it is precisely what made the deuterium bottleneck so severe, and each light element responds to it differently. Deuterium is a leftover, an incompletely burned intermediate. The denser the universe, the more thoroughly it is processed onward into helium, so the surviving deuterium falls steeply as the density rises. This steep, one-way dependence is what makes deuterium the premier cosmic baryometer. To test the theory, astronomers must measure these primordial abundances as they were before billions of years of stars altered them. And stars are the enemy of such measurements, for they both destroy some light elements and manufacture others. The strategy, therefore, is to seek out the most chemically pristine places that can be found, gas and stars with the very lowest abundances of heavy elements, taken as a proxy for the least processed material, and then to extrapolate to a hypothetical composition of zero enrichment. Deuterium is sought in the most metal-poor gas clouds in the distant universe, helium in the pristine gas of faraway dwarf galaxies, and lithium in the atmospheres of the oldest, most metal-poor stars in the halo of our own galaxy, ancient stars that formed from nearly primordial material and have preserved a memory of it ever since. Each element demands its own painstaking technique, and each carries its own uncertainties. Deuterium provides the cleanest test of all, because it is only ever destroyed inside stars and never created in any quantity, so any deuterium found in a near-pristine cloud is a firm gauge of the primordial value. The measurement is a marvel of technique. Astronomers observe the light of a distant quasar as it passes, on its way to us, through an intervening cloud of nearly metal-free gas. The hydrogen in that cloud imprints a strong absorption line on the quasar's spectrum, and beside it, slightly shifted, appears the faint absorption signature of deuterium. Comparing the two yields the deuterium-to-hydrogen ratio directly. Painstaking study of a handful of these ultra-pristine systems has pinned the primordial value down to about 1 part in 100, a deuterium abundance of roughly 2.5 parts in 100,000, measured so precisely that for a time the theoretical prediction could not keep up with the observation. Helium is measured in a quite different setting, the glowing clouds of ionized gas that surround hot young stars in metal-poor dwarf galaxies. The light of such a cloud carries bright emission lines from both hydrogen and helium, and their relative strengths reveal the helium abundance. But because stars themselves also make helium, the measured value in any one galaxy is slightly contaminated by later stellar production, so astronomers plot the helium against the amount of heavier elements across many galaxies and extrapolate back to the pristine, zero enrichment limit. Modern surveys of these regions yield a primordial helium fraction clustering close to 0.245, in gratifying agreement with what the theory predicts. The dominant uncertainties here are not statistical but systematic, rooted in the intricate atomic physics of how helium emits its light, and it is the reduction of those systematic errors that occupies the astronomers who pursue this measurement. Lithium is the subtlest, and as it turns out the most troublesome case. It is measured in the atmospheres of the oldest stars in our galaxy's halo, stars so ancient and so poor in heavy elements that they are nearly first generation. In 1982, the astronomers Francois and Monique Spite discovered something remarkable. Across a wide range of these old, metal-poor stars, the lithium abundance is very nearly constant, forming a flat shelf now called the Spite Plateau. That constancy was naturally read as the fingerprint of primordial lithium, the same everywhere because it was made in the Big Bang before any star existed. The plateau sits at an abundance of about 1.5 parts in 10 billion. It is a beautiful result, but it carries a sting, for that observed value lies a factor of roughly 3 below what the theory of nucleosynthesis predicts, and therein lies one of cosmology's most stubborn puzzles. The crowning test of the whole theory arrived with the satellite mapping of the microwave background. The Planck satellite measured the cosmic density of ordinary matter with exquisite precision, reading it not from any nuclear reaction, but from the pattern of sound waves frozen into the background radiation at an age of some 380,000 years, physics utterly independent of, and hundreds of thousands of years removed from, the first 3 minutes. Feed that independently measured density into the equations of nucleosynthesis, and out come predictions for every primordial abundance. The predicted deuterium matches the value measured in the distant gas clouds almost exactly. The predicted helium matches the dwarf galaxy measurements within their uncertainties, that 2 utterly different probes, the light elements forged in the first minutes, and the sound waves imprinted 400 millennia later, agree on the density of cosmic matter to better than 1%, is among the most impressive quantitative triumphs in all of science. The one glaring exception to this harmony is lithium. For the matter density that Planck measured, the theory predicts about 3 times more lithium than the old halo stars actually show, a discrepancy far too large to wave away, and one that has resisted resolution for decades. 3 broad explanations are debated, and honesty requires flagging this as a genuinely open problem rather than a settled one. Perhaps the ancient stars have quietly destroyed some of their own surface lithium over their billions of years of life, mixing it down to hot interior layers where it burns. Yet the very flatness of the spite plateau sits awkwardly with processes one would expect to vary from star to star. Perhaps some nuclear reaction rate has been mismeasured, though intense laboratory effort has found no error large enough, or perhaps some exotic new physics is at work, though such solutions tend to spoil the beautiful agreement of deuterium and helium. The consensus leans tentatively toward the stars themselves being the culprit, but no explanation is established. Beyond weighing the ordinary matter of the cosmos, nucleosynthesis serves as a sensitive probe of the fundamental physics of the first second, most beautifully, of how many kinds of lightweight particle the universe contained. The logic is elegant: more species of relativistic particle means more energy, which means a faster expansion, which means the weak interactions freeze out earlier, at a higher temperature, leaving behind a larger share of neutrons, and therefore more helium. The primordial helium abundance is thus a direct readout of the expansion rate of the early universe, and historically it provided the first cosmic count of the number of neutrino families, in striking agreement with the value of 3 later measured in particle accelerators. To this day, both nucleosynthesis and the microwave background independently confirm that there were just 3 light neutrino species, sharply limiting any hidden extra radiation that some theories of new physics would predict. 2 further inputs show how intimately nucleosynthesis is now entangled with laboratory physics. The first is the lifetime of the free neutron, which governs how many neutrons survive to make helium, and which is the subject of a genuine, unresolved experimental puzzle. 2 methods of measuring it disagree. Experiments that trap ultra-cold neutrons in a bottle and count the survivors give a lifetime about 8 seconds shorter than experiments that count the decay products in a neutron beam, a gap several times larger than the stated errors, and no one yet knows why. The second input is the set of nuclear reaction rates. For years, the largest uncertainty in the predicted deuterium abundance came not from cosmology, but from a single reaction rate, until a team working deep beneath a mountain in Italy, shielded from cosmic rays, measured it with new precision, and in doing so sharpened the whole comparison and brought the nucleosynthesis density into still finer agreement with the microwave background. Step back and the achievement is staggering. From a single number, the ratio of baryons to photons, the theory of Big Bang nucleosynthesis predicts the primordial abundances of deuterium, helium and lithium. The measured deuterium and helium match those predictions for one consistent value of the cosmic matter density, and that value agrees to better than a percent with the entirely independent measurement from the microwave background. This one concordance accomplishes 3 profound things at once. It confirms the hot Big Bang model back to an age of about 1 second. It weighs the ordinary matter of the universe, revealing that baryons make up only about 5% of the total, and merely a sixth of all matter, which means the rest of the matter holding galaxies together must be something else entirely, the unseen dark matter, and it tightly constrains any new physics operating in that first second. And yet, in the honest spirit that ought to govern all science, the open questions must be named alongside the triumphs. The lithium problem, that threefold excess of predicted over observed primordial lithium, remains genuinely unresolved, a small thorn in an otherwise seamless theory. The neutron lifetime puzzle persists in the laboratory, feeding a real if modest uncertainty into the predictions, and nucleosynthesis, for all its reach, has little to say about the great outstanding debates of cosmology, the disagreement over the expansion rate, the identity of dark matter, the nature of dark energy, which lie beyond its scope. But its enduring lesson is as much about method as about the early universe, that a theory rooted in well-understood nuclear physics, applied to the first minutes of time and confronted with painstaking measurement, can yield predictions of breathtaking precision. Where it succeeds, it lends its confidence to the whole cosmological edifice, and where it strains at lithium it points, as good science always does, toward physics we have yet to understand.